Hello and welcome to the first lecture of space science, and we're talking about some brief history of astronomy. One thing I like to start off thinking about is, what is our place in the universe? Are we really significant? Is Earth really the center of everything? And is there other life out there? If there is, how far away is life? How could we get to it? How can they get to us? Why do we see the moon in different shapes, which we'll talk about later? How far is the closest star, which we will talk about soon as well. And I find those great questions just to sit and stew, think about. Are we really all that important? So just think about that as we move on in the class. Here's a little picture to give you some perspective as far as your place in the universe. This is the Hubble Deep Field. And what happened was the Hubble Space Telescope was turned in a very specific section of the sky and recorded images in 2003 for a couple of months, and then all those images were compiled into one composite photograph, which is this one. And every single speck that you see in this photo is a galaxy, an entire galaxy. And I think in this one picture there are 10,000 galaxies that were captured. And what it allowed us to do was to see further in space than we had ever seen before. And that brought us closer to the galaxies back from the Big Bang. So when you think about that, when you think of there are billions of stars in one galaxy, and there are potentially billions of galaxies in the universe, and our planet just revolves around one star in one galaxy. What does that mean to you? Astronomy, the word means law of the stars, or law and order. Sorry, my dog was barking. And astronomy is the science that studies the universe. It includes observations and interpretations of celestial bodies and phenomena. The Greeks were some of the scientists of the golden age of early astronomy, and they used lots of philosophical arguments to explain phenomena, but they also did use some observational data. They had used a lot of geometry and trigonometry, as you're going to see, to figure out distances, and in a way that no one had ever seen before. Before them, before the Greeks had really started this in the Golden Age, which was about 600 BC, you had the Chinese, you had Egyptian, Babylonian people who would watch the sky and take notes. And a lot of cultures who were dependent on the weather believed that these objects in the sky would control the seasons. One example in your book was the Chinese had recorded Halley's Comet coming. They had recorded every appearance of Halley's Comet for about 10 centuries. So that's about 1,000 years. What they didn't realize was it was the same comet that kept coming every time. Every 76 years, Halley's Comet appears. But they had really good notes back then, the Chinese. Here is a tool that the Greeks had used for trying to find out, using geometry again, trying to figure out the positions of the sun and other stars in the sky. Aristotle was a Greek philosopher who had concluded that the Earth is spherical because it always casted a curved shadow when it eclipsed the moon. And although most of his teachings were passed along, his beliefs in a spherical Earth were actually abandoned during the Middle Ages. Many astronomical discoveries have been credited to the Greeks, and in fact they came up with the geocentric model. Geo meaning Earth, so the moon and the sun and the known planets at that time, which were Mercury, Venus, Mars, and Jupiter, all orbited the Earth. And beyond the planets was this transparent hollow sphere, which was called the celestial sphere, and the stars would travel around the Earth on this sphere. We now know that's not the case because the Earth rotates. And I'll come back to that, but then you have the heliocentric model, which says that Earth and the other planets would orbit the Sun. Helios meaning sun. So here's an example of what a geocentric model would look like in this celestial sphere. An artist's rendering of a geocentric model here, heliocentric model here. Alright, so Eratosthenes was the first Greek to calculate the size of the Earth, and so he had observed the angle between two cities north and south of each other. So don't worry, I'll go back. So notice there, you have your two cities. He noticed that they were 7 degrees apart, north and south. So 7 degrees, he concluded, was 1/50th of a complete circle. And by the way, the Greeks thought that the circle was a pure and perfect symbol or shape. So they often worked with circles. So 7 degrees is 1/50th of a circle. He concluded that the circumference of the Earth must be 50 times the distance between those cities. So he had calculated that the Earth was 39,400 kilometers across, and the modern day value today is 40,075. So that's pretty darn close. And so again, he was using kind of this new method of geometry, and I think it's kind of fascinating because I wouldn't have thought about that. Another early Greek astronomer was Hipparchus, and I don't have a slide for him in here, but he was known for cataloging 850 stars, their locations, and he had cataloged them according to brightness. So he had measured the length of the year to within minutes of the modern value and developed this method for predicting the times of lunar eclipses. So another huge contribution to astronomy from a Greek. The Earth-centered view, the geocentric view, was really brought to the forefront by Ptolemy. And Ptolemy was really credited with proposing a working model of the geocentric model, and he had believed that the celestial sphere made a daily trip around a motionless Earth. So does the Earth move? Yes, it rotates on its axis. In addition, he had proposed that the Sun, Moon, and other planets made trips of various lengths along their own individual orbits. So depending on how long the orbit was going to determine how long it took to go around the Earth. The motions of the planets when you see against the background of stars is not really so simple, because as he has all the planets going around the Earth in one orbit, they're still going at different speeds. And retrograde motion is an apparent motion, meaning it doesn't really happen, but the way that it looks, it appears to move. So what happens is that each planet is moving eastward among the stars along the backdrop, and periodically it looks like it's going to stop, reverse direction for a little while, and then resume going back eastward. That is called retrograde motion. So what causes this apparent motion is the fact that Earth has a faster orbital speed than Mars. It is closer to the Sun than Mars, therefore its orbit is shorter and it's going to travel faster. So an analogy for that is if you're in a race car and you look out of your side window when you're passing a much slower driver. Have you ever seen that instance where it looks like the car next to you is going backwards when it's actually still moving forwards? It's just going slower. This diagram shows you what it looks like. So you have the planet going along its orbit, and then once it gets to about here, it looks like it's going backwards. It looks like it's experiencing retrograde motion and then keeps moving forward. Okay, so again, it's because Earth is moving faster around the Sun than Mars due to its shorter orbit. Unfortunately, I don't have the graphic here, but if you look in your textbook on 494, you'll be able to see how Ptolemy had proven, quote unquote, proven his model, because he put each planet on these smaller circles called epicycles going in or revolving around larger circles. And so he was able to figure out these combinations of circles to produce how much retrograde motion each planet had. And this is a case where he was able to do enough math to fit and manipulate that math to fit his model. So because he had the math to support him, it was supported by the community. Then you have Copernicus. So we had Ptolemy in 141 AD, and then it just kind of stayed there for centuries. And then modern astronomy really was evolving during the 15 and 1600s. And so the first astronomer to emerge out of the Middle Ages was Nicholas Copernicus. He was from Poland, and he had become convinced that the Earth is a planet. But he said that the motions of the heavens, the stars moving about, could be better explained by the fact that the Earth rotated and not everything traveling around the Earth. He suggested that a much larger celestial sphere would be more likely to fall apart if it actually had to rotate, as Ptolemy had said. So he said that the Sun is in the center of the solar system. So he was the first proponent of the heliocentric model. And he said that planets travel on elliptical orbits instead of perfect circles, because the predicted locations and observed positions of planets and stars did not match if you put them on perfect circles. Some Greeks probably didn't like that because they weren't perfect circles, so it wasn't a pure shape, but ellipses would better fit a mathematical model. Tycho Brahe was a Danish astronomer who was born after Copernicus had passed away, and he had designed and built these pointers that would measure the locations of certain heavenly bodies like stars. At this time, which was the mid 1500s or the second half of the 1500s, there were no telescopes yet. So his instrument was called a pointer. He actually didn't believe in Copernican theory because he couldn't see this apparent shift in the position of stars that would have been caused by Earth's motion. And his argument said, if Earth does revolve around the Sun, the position of a nearby star, when observed from extreme points in Earth 6 months apart, should shift with respect to a more distant star. The idea was correct, and this apparent shift was called parallax. The idea of parallax was correct, but because the distance to the nearest star is enormous compared to the width of the Earth's orbit, the shift that would occur is too small to be seen using the very first telescopes or your unaided eye. You have to have a large mirror or lens telescope to be able to see parallax in action. But you can enact it right now. So if you hold out your finger or your thumb, hold it out in front of you, and then close one eye and look at it, and then switch your eye closed. So first you'll close with the right, and then you switch to the left. Okay, you may not see that your finger has moved very far. Bring your finger a lot closer to you. Do it again. Close one eye, then switch to the other one. It looks like it's moved a lot more when it's closer to you. So the closer the object is, then you can see parallax more easily. But again, parallax is an apparent motion. So in 1601, Brahe had died, and he had an assistant the last year of his life named Johannes Kepler. And Kepler had kept most of his observations, most of Brahe's observations. And what's interesting is that Kepler had used this data that Brahe had to not refute Copernican theory, but to support it. And it was Kepler who came up with the 3 laws of planetary motion. Before that, let me go back to what Tycho Brahe's observations of Mars. What Kepler ended up saying was he had discovered from all of Brahe's observations of Mars that the orbit of Mars was not a perfect circle, but is elliptical, and that he realized that the orbital speed of Mars does vary or change in predictable ways, meaning that as Mars would approach the Sun, it speeds up, and as it moves away from the Sun, it slows down. So we'll talk about that in a second. So those observations of Mars that Brahe had written had helped Kepler come up with his first 2 laws, that the orbits of the planets are elliptical with the Sun at one focus. So one thing for you to see, if you see in this diagram here, the Sun is not directly in the center. It is actually off to one side. That is the focus of an ellipse. Okay, I'll come back to that. Planets will revolve around the Sun at varying speeds, and there is a mathematical proportional relationship between a planet's orbital period and the time it takes to go around the Sun and its distance to the Sun. An ellipse is an oval-shaped path. And the astronomical unit, or AU, is the average distance between the Earth and the Sun. that is a number you will have to memorize. So 150 million kilometers or 93 million miles is between the Earth and the Sun. So let's look at this again. This model would basically work for any of the planets, but we can pretend that this right here is Mars. So notice you have the Sun at one focus and the planet is going around the Sun. So notice here it says faster. What would cause the planet to go around the Sun faster in these winter months? If you said gravity, you would be correct. So as it gets closer to the Sun exerts its gravitational force to pull it along its orbital path faster. And as it gets to the other side during our summer, it goes slower because it is further away from the Sun. Also, keep in mind that for the northern hemisphere people, if it's going around the Sun faster during the winter months, what does that mean for our daylight hours? We have shorter daylight in the winter months, and as it travels slower around the Sun in the summer, we have longer days. So after Kepler came Galileo Galilei, and he was an Italian scientist, and he was a contemporary of Kepler, so he was working at the same time as Kepler, and he did support Copernican theory, which supported sun-centered or heliocentric solar system. And so his greatest contribution to science were the descriptions of behaviors in moving objects that he had gotten from experimentation. He had also discovered or developed his own telescope, and from his telescope he made these 5 important discoveries: that there were 4 satellites or moons that orbit Jupiter. And so what this did was show us that the Earth was not the only center of motion, because for another planet such as Jupiter, things were going around that planet. So Earth was not the center of everything. Planets are circular disks rather than just points of light, and so this indicated that planets must be Earth-like. He also discovered that Venus had phases like the moon. So what would that show? That would show that Venus orbits its own source of light. So notice in this picture on the left, you have a geocentric theory, which doesn't really fit with having all the phases. Notice that you can't have all the phases here. But in this heliocentric theory, and you see as Venus goes around the Sun, it has phases. And then these are actual photographs of phases of Venus. So that further supported the heliocentric theory. He had also discovered with his telescope that the moon's surface is not smooth and glassy, but he had discovered craters, big spots. He saw mountains, he saw plains. He thought maybe that the plains were bodies of water, which is why they called them, those huge plains, the sea of something, the sea of tranquility, the sea of storms. That came from Galileo. And then finally he had discovered that the Sun had sunspots. And we'll talk about that later, but a sunspot is a darker, cooler region on the Sun. And he had tracked movement of those and discovered that there was actually a rotational period of the Sun, because the locations of these sunspots were very predictable. Unfortunately, he had gone blind looking at the sun, and his discoveries really weren't well supported by the community. It was against a lot of the religious doctrine at the time, and so because of that, and it went against the Ptolemaic system, or Ptolemy, he was tried and convicted, and sent to permanent house arrest. And house arrest is where at home is where he died 10 years later, after he'd become totally blind. In 1992, Galileo was finally exonerated from his crimes by the church. Then that brings us to Isaac Newton. And we're all familiar with Newton's apple. And some had even said that Newton was the greatest genius that ever existed. This was the excuse me, second half of the 1600s and early 1700s when Newton was around. That's my phone. Well, let me go back for 1 second. Kepler had believed that some kind of force had pushed the planets in their orbits. Galileo said that no force is actually required to keep an object in motion. Galileo said that the natural tendency for a moving object is to continue moving at a uniform speed and in a straight line as long as it's unaffected by an outside force. So this concept of inertia was later formalized by Newton as his first law of motion. Remember, the first law of motion is an object in motion stays in motion, and an object at rest stays at rest unless acted on by an outside force. And so the problem was not to explain the force that keeps them moving, but what force keeps them from going in a straight line, to keep going in its natural tendency. And that's when he got gravity. And so he formalized this law of universal gravitation that says every body in the universe attracts every other body with a force that is directly proportional to their masses, so you would multiply, and inversely proportional, which is divide, to the square of the distance between them. So for an example, if two objects were 3 kilometers apart, the gravitational force would be 9 times. So the greater the mass, the greater its gravitational force as well. We know that from the sun. The sun, the biggest object in our solar system, it is what affects the planets going in orbit. So basically, the two motions, the two, forces, or influence on planets and keeping them in their orbits are gravity and inertia. Inertia is what keeps the planet going in its orbit, and gravity is what kind of pulls it down. So if you look at this right here, as the planet is going along its orbit, its natural tendency, and this is inertia, is to go off in a straight line. Go off in a straight line. Go off in a straight line. But it's the gravitational pull from the sun that draws it back into its orbit. Okay? So, the two influences on planets staying to their orbits are inertia and gravity. Finally, perturbation, which I know is a funny word, is any variance in the orbit from its predicted path. And this was kind of like the idea of retrograde motion, except it's about 2 planets perspective from each other. So what you see in this illustration is two planets orbiting a star. And you could look at it as Mars and Earth orbiting the sun. When the planets are at A, the outer planet exerts a gravitational force that accelerates the inner planet, which makes that body move faster and ahead of that normal path. When the planets had reached B, the reverse is actually true, and the inner planet is slowed down or decelerated. And so it changes its path and slows down. So it's because these planets move ahead or behind one another relative to each other, it was that led to the discovery of planet Neptune. Okay, this is where we're going to end this first lecture. You might need to rewind if you have to fill in some of your notes. And as always, let me know if you have questions. Thanks.